Now, this is the second part of the lecture, and I continue with introducing Gauss's divergence theorem to you. And what I'm going to look at is, I'm going to look at the flux through a closed surface. And let's look at it. We have, say, this solid in space. So I could indicate that it is a solid in space. And together with that, we have a normal vector field to the surface. I think I'll do this in red. You have outward pointing at every point. You have this outward pointing normal field. So I could write here that the surface is oriented by an outward pointing unit normal vector field. Okay. So I could say that the flux out of this surface is equal to the flow per unit time out minus the flow in. So if the flux is greater than 0, then there is a netto expansion. And you're talking about having a source. If the flux is less than 0, then there is a netto contraction. And you have a sink. And now I will give you a divergence theorem. So, given a solid spatial region, and I denote this omega, then the flux out of the boundary of this region, and this is the boundary of the region, the flux is equal to the volume integral across the region of the divergence of the vector field. So this is a two-dimensional. The first one is the left-hand side is a two-dimensional integral, and the right-hand side is a three-dimensional integral. And as such, it could be more complicated to evaluate. But if the divergence is a simple function, then it might be it might be easier to evaluate the right-hand side rather than the left-hand side. You know that the divergence of the vector field V is equal to the x derivative of the first component of the vector field plus the y derivative of the second component of the vector field plus the z component or the z derivative of the z component of the third component of the vector field. And if you will have an idea of what is the divergence, then look at the lecture Maple demo. Look at the lecture Maple demo. And this is uploaded together with these lectures. Now, I'll start this by giving an example. We're given a vector field and this is minus x plus cosine c or z, cosine z, minus y times x, and then 3z plus the exponential of y. So this looks pretty complicated. And a solid region omega, and this is the set of points where x is in the interval from 0 to 3, y is in the interval from 0 to 5, and finally z is in the interval from 0 to y squared. And the question is, determine the flux through the surface of the region omega. Well, first, it's a good thing to look at at the region, or omega. So let's try to do that. I draw here. See if I can draw this. This is z-axis. Draw it a little bit longer. And then you have the y-axis here. And then you have the x-axis in this direction. You see that x is going between 0 and 3, and y is going between 0 and 5. So this is the area in the xy plane. And then the set is going between 0 and a parabola that depends on y. So it will be, if I'm not using the same scale in the set direction. So if we have this, then we have this parabola. So this is actually, the height here is 25. And then again, you have this parabola. So this will be your omega. So I write here omega. Okay, so now I can do more things. There's method 1, where you actually calculating the flux out of each of these surfaces. So you should calculate the flux out through 5 surfaces, and then add the things together in order to get the total flux. Well, I would say no thanks to this. It's simply too much to do this. The second method is that you use Gauss's theorem. And we'll do that, but let's look at the divergence of your vector field. So you have to take the divergence of, or the derivative of the first component in V with respect to x, that will be -1. And then with respect to y of the second component, that would be -x. And then with respect to z of the third component, that will be, with respect to z, that will be 3. So if you add this all together, you get the divergence is equal to 2 minus x. This is a fairly simple divergence, so let's see if we can use this. Well, you see that the foundation of omega in the xy plane is a rectangle, axis parallel rectangle. So I can actually use x and y as parameters. I only need a third parameter in order to describe the whole thing. So I use x equal to u, and here v equal to, or y equal to v. And here u is in the interval from 0 to 3, and v is in the interval from 0 to 5. And then the z component, you use a third parameter times y squared, because when y is 0, you get that z is equal to 0, and when w, or when w is 0, you get z equal to 0, and when w is equal to 1, you get y1. So you get that w is equal or is in the interval from 0 to 1. Now, this is the volume integral. So you have to compute the Jacobian of your corresponding to your parametric representation, and you have, let me write down the parametric representation, and it's say it's a function of u, v, and w, and it is equal to u, comma v, comma, and then w times v squared. And with the previous given parametric range, or the range for the parameters. So the Jacobian would be the numerical value of the determinant of this matrix, where the first column is r prime u, the second column is r prime v, and the third column is r prime w. So this will be equal, and then the numerical value of this, it will be equal to the determinant. When I compute this, I get 1, 0, and then 0, and then I get 0, 1, 2, w, v, and then I get 0, 0, and then v squared. And this is easy to calculate because you have a 1 here, and then, well, it's a lower triangle long matrix, so the determinant is a product of the elements in the diagonal, and that will be v squared, and v squared is a positive or a non-negative quantity, so this is actually the Jacobian. So let's see. Now, instead of doing all these different surface integrals, I can do this triple integral. I integrate w from 0 to 1. I integrate y from 0 to 5. And then I integrate u from 0 to 3. And I have the restriction of the integral, which is a divergence, that is 2 minus x, so that will be 2 minus u, and then times v squared, du, dv, dw. So it will be 0 to 1, 0 to 5, and then you have the integral here is 2u minus 1/2 u squared, and this should be taken between 0 and 3. And then you have your v squared times v times w. So this will be, say, 3/2. This is this parenthesis evaluated. You can put this outside your integration, and then you have the integral from 0 to 5 of b squared dv times w. So that will be 1/3 v cubed, and so that will be equal to, and it doesn't depend on w, so that will be just a 1. So you have 3/2, and then you have v squared from 0 to 5, or v cubed, third, and then this will be 125/2. So this is the flux. I end up with another example, proving or showing a special version of, say, the Gauss theorem. Now we are given Vx comma y comma z is this vector field, x comma y comma z, that is, normally this is called the explosion vector field. And also we are given the solid sphere with center at in 0, 0, 0, and radius r. Okay, so we have this situation. We have in an x, y, z coordinate system, we have this sphere here of radius r, and then we have this explosion vector field pointing away from the origin. Now, if we calculate the divergence of this vector field, we get 1 plus 1 plus 1, that is equal to 3. So we have a constant vector field, and this is then very easy to compute, because then we have that this flux integral is equal to the volume integral of the divergence of the vector field V. And since the divergence is 3, you get, this is constant, you can put it outside, and what is left as the integrand is a 1. And remember, when you integrate 1 across this volume here, or this region here, you get the volume of omega. Now, you could either compute it or look it up, or maybe you can remember, but the volume of the sphere of radius r is 4/3 pi times r cubed. So the result is 4 pi times r cubed. And this is, in fact, this gives rise to a special version of the Gauss divergence theorem. So if you're given a vector field with the divergence of the vector field equal to a constant, you can call this constant A. It applies for every omega that the flux adds through the surface of omega is equal to A times the volume of omega. So we could call this the spatial Gauss theorem. So this is the end of the lecture today, and I think that you are now well prepared to do the exercises this afternoon, and then again you will be prepared for the weekly test. So please do the exercises and do the weekly test. Thank you.